Defense startup Furtherium has been working on the augmented reality head-up display full-face mask ARHUDFM project since 2021. The ideas and research behind it originated in 2015. However, at that time, the state-of-the-art, capabilities, size, and cost of the components did not yet meet expectations. Currently, and in the near future, we intend to finalize the R&D package to move to pilot production and launch proving ground tests in 2026 with the U.S. Marine Corps and U.S. Army. Our strategic plans include robotic manufacturing, capable of providing the majority of U.S. and NATO military personnel with low-cost, reliable, secure, state-of-the-art, and continuously evolving open-source technology for partners within 6 to 10 years. We would like to thank the experts at the National Geospatial-Intelligence Agency for their interest in the project. Military, police, firefighters, and physicians have supervision, super hearing, super respiratory and facial protection, a built-in drinking system, an advanced communication system, and various digital assistants using augmented reality, artificial intelligence, computer vision, computer audition, voice control, hand tracking, and vitals body sensors. Briefly, is AI-powered tactical situational awareness mobility platform. It's a dual-use technology. Our solution is a full-face mask and SaaS that increases a user's human capabilities and situational awareness, creating tactical advantages on the battlefield, firefighting, human rescue, and security. The project ecosystem includes groups of functions: situational awareness, communications, navigation, intelligence, surveillance, reconnaissance, firing assistance, task management, respiratory and facial protection, vitals, body sensors, and care under fire, safety and protection of user health. Key users' pains: fog of war, friendly fire, BLOS comms for everyone, fire contact range, drones and robots, RF space, all threats detection, night vision, one shot, one hit, soldier as sensor. The company has 2 co-founders and 5 mentors whose expertise and skills create engineering innovations to bridge the gap between existing DoD agency requests and off-the-shelf solutions offered by contractors. Electronic headset must meet the requirements for continuous use, safety for the user, protection of collected and transmitted data, protection from environmental factors and external influences, as well as for the possibility of remote administration and updating the software code on the devices. We primarily proceed from engineering advantages in design and development, in the possibility of quick repair, upgrade, in increased reliability, in reduced heat dissipation and power consumption, in reasonable division of tasks and computing power, in reduced size and weight. The device has a modular structure, such as a main computing module, a neuromorphic computing module, a projection module, a base controller, a video controller, an audio controller, a software-defined radio, SDR controller, a software-defined antenna, SDA controller, a power controller, and other modules. We have a long and careful history of researching user problems along with analyzing technical solutions, including keeping abreast of news and innovations from technology companies. We have participated in innovation requests from various DoD, DARPA, DIU, USACOM, U.S. Marine Corps, U.S. Army, U.S. Navy Office of Naval Research, and U.S. Air Force agencies since 2023. In his speech at AIPCon 5 at Palantir Technologies on September 12, 2024, Vice Admiral Frank Whitworth emphasized the importance of AI in shaping superiority in theater analysis and decision-making. We too hold this view, and in our technology, most of the functions use AI. However, we want to emphasize that big data systems like Maven Smart System, Convergence, other CJADC2 and C5 ISR systems are or will be placed in command posts, decision centers, and integrated into modern combat vehicles. Overall, this is not a comprehensive solution, and it is insufficient because it doesn't provide the necessary sensor coverage and confirmation speed for decision-making, nor the necessary delegation for independent decision-making. In our opinion, to fully satisfy big data systems need integration with a multimodal end-user solution, client-server integration, a mobile platform with ISR and AI capabilities that can be used by every user, infantry units, and operators of over 90% of the less than state-of-the-art combat equipment that is in service and will be in service for years to come before being replaced by newer equipment. Our solution is also an element of the soldier as sensor concept and is ready for the key role drones, robots, and unmanned vehicles will play on the battlefield in the future. We'd like for you to check out the 16-minute overview demo video on our website for 10 of the most important of the 30-plus features. But today, we're only going to introduce 2 of them, Gunfire Locator and Radio Direction Finding. Gunfire Locator, GFL, is a separate function within the Computer Audition subsystem with broader capabilities that include detecting, collecting, logging, analyzing, filtering, modifying, recognizing, machine learning, reporting to the user, transmitting reports to the server, and to other users within peer-to-peer and other mesh networks. Computer Audition provides several complex scripts that can be used simultaneously. Detect noises of aircraft motor, exclude sounds of nature, eliminate echo, detect noises of human activity. Gunfire Locator, active noise reduction. The Gunfire Locator sensors include 13 microelectromechanical systems, cardioid directivity diagram microphones in a dome array. The narrow radiation pattern allows the system to be more accurately tuned using the amplitude triangulation method by shifting the peak power of the input signal on different sensors. The dome sensor array registers not only the direction of the signal, direct of approach, DOA, for each sensor, but also using triangulation, more precisely, triangulateration. The distance to the signal source is calculated. Triangle sum theorem plus geodesic surplus, trigonometric calculations. In addition, the phase triangulation method is used to improve accuracy. In this case, the phase difference of voltages of several sensors is calculated, taking into account their directionality and distance between them. The accuracy of the phase method depends on the sampling rate of the audio signal, which is delayed to different sensors with a fixed directivity diagram, located at a fixed distance from each other. Sampling, for which the ADC of the device is responsible. The higher the sampling rate, the more accurate the angle can be calculated. In the future, when improving the computer audition system, we will conduct additional experiments on acoustic beam steering, phase triangulation method, while increasing the elements of the sensor array. This will allow, if necessary, to increase the accuracy. The audio controller registers audio signals incoming to the sensors and provides operation of the integrated multimedia system, user microphones, headphones, external devices, electronic push-to-talk, control of electromagnetic flaps for protection against loud sounds and confusion from a trailing blast wave. The device's basic controller, accelerometer and gyroscope, GNSS sensor and other sensors, including Hall sensors and thermometers, provide data to accurately correlate the audio controller's relative measurements with absolute measurements of geolocation, position, self-speed, and direction of motion in 3D space, environmental conditions, pressure, relative humidity, that are important to the calculation. The audio controller uses a 14 or 16-bit multi-core ADC for signal processing and time registration. This is important for the sampling rate as well as the quality of pattern detection and recognition for subsequent machine learning. The GFL control software application on the main device analyzes several data streams. The oscillogram of combined and separately selected sound waves by ML filters, directional patterns, sound wave AFC, and waterfall characteristic patterns for identification of belonging to the source, preloaded pattern library, pre-training on the device. The Doppler method in the GFL software application is additionally used to determine the direction of the sound wave relative to the measurement system, approaching, distant, or equidistant position of the source during the time period of a single and repeated sound signal, sound of the ammo moving along the ballistic trajectory, as well as firing in motion or from a stationary firing position. The Doppler method, together with the above data from the controllers about the position and motion of the sound wave source and the user in the mathematical model, refine the measurements. Individual patterns characteristic of different and similar types of weapons, muzzles, ammunition based on ML models allow for to identification, respectively, firearms and ammunition. Sufficiently well-studied methods and techniques can accurately distinguish between the user's own shots, friendly fire, posing or not posing a threat to the user, and hostile fire, posing or not posing a threat to the user. The technology analyzes shot and launch data from all types of throwing and reactive weapons, not just small arms fire. Timely and more accurate acoustic range data will allow the user to get a hint of an immediate threat and the ability to respond to it, or the absence of an immediate threat and the ability to reduce unnecessary stress. The GFL application is integrated with other applications on the device, including the Instant Messaging System, IMSG, which separately displays minimalistic information on the screen about firing threats, indicating the direction, distance, caliber, and serial number of the firing of a given source. The IMSG message also includes the unique ID of the shot source, friendly, hostile, etc., from the navigation grid, Identification Friend or Foe, IFF system. This helps improve navigation during combat. An additional service feature is integration with a logistics application that keeps track of the user's own shots and displays the stock in the current magazine and the user's total ammo stock. The stock data is transmitted to the big data system to ensure timely delivery of ammo by drone or robot if necessary. Consideration should be given to that most shots have a supersonic velocity at the exit from the muzzle of small arms and artillery weapons, 2 to 3 times higher than the speed of sound. It's the registration of the sound wave of overcoming the sound barrier, sound of flight, or sound of a head wave, that is often more important than the sound of powder gases exiting the barrel, sound of salvo, especially when firing with a silencer. Depending on the distance, the sound wave front of the shot, salvo and ammunition flight, may overtake the ammunition in the 3rd to 6th second of flight. The speed of the sound wave may sometimes exceed the average flight speed of the ammunition at medium and especially at long ranges. But even if this does not happen, when the arrival time of the sound wave is longer and the ammunition reaches the target before the sound wave arrives, it is rare that the target is hit from the first shot. Therefore, users are left with several options for responding to subsequent shots. Registering a shot that poses a threat to the user triggers an instantaneous audible and visual alert as perceived by the user, with simultaneous indication on the navigation grid of the detected identified source, ammunition type and caliber, direction, and distance. Factors of rate of fire, ammunition, distance, and likely accuracy of fire, aimed, sniper, or disturbance fire, affect the user's response. Take cover, change body position, return fire. Depending on the distance and whether the user is allowed to return fire, the firing assistance application helps the user to aim at a detected target in the auto-target list in a couple of seconds, corrects the fire, and records confirmation of target destruction by visual methods. We would like to emphasize the situation with sniper fire, which is usually conducted from a concealed position by single shots followed by a change of position. The supersonic velocity of the bullet makes it impossible in most cases to detect, recognize, and localize such a shot until the time of arrival of the ammunition. However, at ranges greater than 400 yards with a moving target, it is very difficult for a sniper to hit the target from the first shot due to many ballistic factors. The time until the fire spotter and the sniper is ready for the next shot is very valuable. Typical behavior for a unit that has come under sniper fire is to lie down or take cover. After that, the unit stops moving for the nearest time and is incapacitated. The survival instinct and the factor of the unknown do not allow to make an effective decision quickly. This is often what a sniper team counts on. However, if the unknown factor is absent, The unit under fire has a unique opportunity to destroy the sniper position with return fire from a grenade launcher before the deadly shot follows. Registering a shot that does not pose a threat to the user also triggers an instant audio and visual alert and an indication on the navigation grid of the source of the shot data. Again, depending on the distance and whether the user is authorized to return fire, the system offers hints that may relate to the probable cause of the identified fire: fire at user-friendly forces, or disturbing enemy fire. The user makes a decision, with the system automatically logging the event and relaying the message to other users. Registering events accurately to each shot also helps the system to learn itself in the future, train the user to use ammunition rationally, and create automated reports for debriefing after the end of the mission. Although when using identification friend or foe in conjunction with firing assistance, the user will be alerted at the time of aiming to the likelihood of friendly or crossfire, the Gunfire Locator system, when registering a shot that potentially poses a threat to the user, will inform all users in the location of the risk and the need to follow the target distribution in firing assistance that eliminates the risk of friendly or crossfire. Registration of the salvo and arrival of a mortar round. Initial velocity 100 to 600 meters per second, terminal velocity 20 to 200 meters per second. Or artillery shell. Initial velocity 200 to 1400 meters per second, terminal velocity 40 to 300 meters per second. At a range of over 2 to 3 miles already during the first shot before hitting the target. A guided strike drone with a barrage munition in almost all cases before hitting the target, or unguided multiple rocket launchers. Average velocity over 1,000 meters per second, almost always after the first inaccurate sighting shot, and with a kill radius, or more precisely, a stopping effect of 20 to 100 yards. All of the above shots give the user a few seconds to assume a different body position or take cover. After an explosion near the threat of concussion, electromagnetic flaps in the earpieces seal off the entrance to the incoming blast wave within less than 3 milliseconds, preventing hearing damage. Active noise reduction when the threshold is exceeded, 85 decibels sound pressure level, reduces sound levels to delta, 80 decibels sound pressure level, protecting hearing, reducing stress, and making it possible to hear audio communications and system messages. Machine learning and high sensitivity of sensors will allow in the future to detect and recognize, among other things, patterns of audio signals preceding the shot, sound of bolt mechanism, turning of firing turret. Radio direction finding, RDF, is a function that is part of the SIGINT subsystem, which also includes software-defined radio scanning, radio frequency drone detection, radar warning receiver control, passive covert surveillance radar, explosive ordnance disposal detection. These functions combine the use of radio frequency spectrum in the wide range of 2 MHz to 8 GHz, HF, VHF, UHF, L, S, C bands, up to 40 GHz, X, Q, K, K bands, and the use of multiband software-defined antenna, SDA, a special case of phased array antenna, PAA, which in addition to SIGINT tasks is also used for communications and remote control for drones and robots. In turn, SDA is based on the use of digital beamforming, DBF technology, without which radio direction finding technology would be inaccurate and inefficient. Digital beamforming is replacing analog all-round and directional RF antennas, which no longer provide the required performance, have significant size and weight, are severely limited to the RF band, often take time to tune, and consume too much power for use in a mobile platform. But most importantly, most of the technologies used in antennas don't meet the requirements of stealth. Existing and future antennas in the Q and K bands, Starlink, Hughes OneWeb, Amazon Kuiper, are already being built using only this technology. The limitations for RF bands from HF to K bands today do not mainly concern the technical design of antennas, but the principles of their use. If, when using an omnidirectional communication antenna, you don't need to orient yourself where other receiving and transmitting points are located, except for complex landscape or atmospheric conditions at long distances. Then, when using a directional antenna, you already need to know the exact coordinates of these points: receivers, transmitters, repeaters, and transceivers. Moreover, the model of communication session becomes more complicated when all users, including the user himself, are in motion, or there are obstacles to the propagation of radio waves. Therefore, directional antennas are generally used to connect fixed communication points, and phased array antenna is mainly used in modern satellite systems and in radars, where relative to the measurement system, ground, marine, aircraft radar, it is necessary to scan the reflected beams. Digital beamforming can be realized at the antenna element level or at the subarray level. In DBF architecture, there are many digital receivers, one own receiver at each of the elements of the antenna. The down-converting to I/F frequency and digitizing the signals is realized at each individual antenna element, or small groups of them. Noise and signal distortion in each receiver is decorrelated among all receivers. Multiple independent beams steered in all directions can be formed in the digital beamforming processor. The benefits of digital beamforming include improved dynamic range, controlling of multiple beams, better and faster control of amplitude and phase. Digital beamforming technology itself is not new and has been used in military, meteorological, aviation, geophysical, and space radars for decades. However, the design breakthrough has only come in the last 5 to 7 years due to research and production of new materials, high-frequency circuit board laminates, composites, assemblies, advanced architectures, fully self-aligned silicon-germanium heterojunction bipolar transistors, 28-nanometer fully depleted silicon on insulator bipolar complementary metal oxide semiconductor, as well as in connection with the development of design and virtual prototyping systems, downsizing of silicon integrated circuit manufacturing processes, and in addition with the development of machine learning capabilities. Stealth two-way communications and data exchange, including in peer-to-peer networks. Passive receive mode, receiver. Active transmit mode, transmitter, including IFF transponder, smart gain, periodic ultra-short sessions, hopping frequencies, and transceiver mode, which provides bidirectional and multidirectional one-to-many radio interface between devices. Scanning of RF space to search, detect, recognize radio sources, communication sessions, drones and robots, their operators, radars, beacons, reflected signals. Direct RF source localization, RDF, and reflected RF source localization, passive radar mode, using an illuminator reference signal, friendly or hostile radar signal, FM, AM, HDTV. Localization of the reflected RF signal source, passive ground penetrating radar, GPR mode, using a portable illuminator reference signal, RF source with a directional short-range signal attenuation pattern. As already mentioned, the stealth requirement is very important when evaluating the benefits of digital beamforming technology. Transmitters that use omnidirectional antennas are increasingly being built using hopping frequency technology. However, this protective measure may not be enough. AI is able to detect and identify different sessions in a short time and combine them into one whole session. This is more labor-intensive, but is feasible. Even without the ability to decrypt the session data, the enemy has the ability to determine the location of the radio source and the likely type of session. On the other hand, in order to meet the requirements of stealth, users must know each other's location, or likely location, accurately, so that the point-to-point beam direction is maintained independent of motion. Secondly, so that the signal gain of the antenna is adapted to the distance, environmental conditions, and terrain. In this way, the probability of signal interception is reduced many times over. The enemy needs to be exactly on the line of the segment between the two connection points and maintain his position on the line, depending on the movement of one of the points. Location information is one of the many basic elements of CJE-C2 technology, in particular the IFF, navigation grid element of the ARHUDFM mobile platform, where location data is transmitted simultaneously via a short encrypted data pack, via periodic IFF transponder sessions to a known comms node, or with a wider beam, covering previous and likely location given direction and speed of travel, via comms sessions, via confirmation after detection by EO/IR sensors of users and ISR devices, aircraft, UAS, land sea vehicles, robots, through acoustic signatures, radar signatures, mission information, and automatic tracking of the user's route. Multiple simultaneous opportunities to maintain up-to-date location information for each user, even in radio silence mode, when a user intentionally fails to respond to a transponder request, but the system reports their likely location, allow users to maintain stealth secure comms, and by eliminating voice data transmission and replacing it primarily with the exchange of compressed digital character data, such comms sessions become very short while improving the quality of data exchange. Beamforming is a signal processing technique to get a directional signal transmission, or reception, from an array of emitters, or sensors. By controlling the relative phase and amplitude difference between the elements, we can shape the emission or reception pattern according to our needs. The underlying physics principle being used here is the fact that, when several sources interact together, they have constructive or destructive interference depending on the direction. We can use these interference patterns to our advantage to choose where most of the energy is sent. The beamforming process of a phased array depends simultaneously on several factors: the gain of each array element, the phase shift, and the signal patterns. With adaptive parameter tuning, the interference properties prevent the signal from diverging to the sides. This is how the beam of the desired directivity and power is formed. The side lobes of the antenna usually have much lower power density. In the interrogation, scanning mode, the beam can shift in each direction by plus or minus 80 degrees. The system consists of 3 modules located at an angle of 120 degrees to each other and 60 degrees to the horizon, dome shape, which allows the user to constantly interact with the RF space in all directions. In passive scanning mode, one or more beams in one band or multiple bands simultaneously analyze the signal-to-noise ratio, SNR, and use machine learning, computer vision techniques to analyze the spectrogram, directivity diagram, and waterfall of signal patterns. If a signal source is of interest, the assignment is typically passed to one of the unoccupied arrays of the antenna array for tracking, while the other arrays continue to scan continuously to detect other signal sources. The direction-finding process depends on the phase shift of the signal beam received by different antenna elements. Accordingly, more accurate angles can be calculated if 3 or more beams with a very narrow radiation pattern, divergence less than 0.1 degrees, are used. For this purpose, a center antenna array of 196 elements is used, allowing 4 to 12 beams to be used. Next, triangulation of the signal beams is performed, using known angles to the base of the beams. Since the propagation speed of RF wave is close to the speed of light, and the distance between antenna array elements is small, a more accurate method for triangulating a direct RF signal from a source is to initially fine-tune the antenna beams to the peak power value of the received signal. In passive radar mode, it is important to accurately localize the source of the direct RF signal, acting as an illuminator, and then localize the source of the reflected signal. After time of arrival, TOA, detection of similar patterns in the reflected signal, and triangulation of the reflected RF signal source, the exact direction and distance to the reflecting object is determined using the same method, and the signal signature is analyzed to identify the type of object: size, shape, metal, water, human. In the case when the RF signal source is located far away, to refine the triangulation angles can be used to synchronize the devices of 2 or more users at a distance of several yards or tens of yards. The system gives hints, to reduce the error of calculating the coordinates of the object. This is a well-known and widespread method of RF triangulation, including how passive multistatic radar works. The EOD scanner GPR method is implemented in much the same way as in the last example, as in the case of active illuminator radar, where it is possible to measure the pulse travel time to the reflecting object and from the object to the receiving antenna, TOV, and to compare the signature of the reflected RF signal. This includes allowing computer vision to see the signature and identify suspicious patterns of ground heterogeneity, even if the signature doesn't indicate the presence of metal or liquid concentrations. The difference is that the source of the EOD scanner illuminator's direct RF signal, its position in space, the direction and momentum of the pulse, and the frequency and power of the outgoing RF signal are synchronized with the receiver in the headset. A special case of an illuminator is a form of handheld flashlight that uses an active phased array antenna. The task is simplified by the fact that in this case, it is easier to identify the reflected signal in order to establish the direction and distance to the object reflecting the signal, in this case surface mines and slightly buried mines, including both metal and plastic-clad mines, with liquid explosive, metal fuse, unexploded artillery and mortar shells, directional mines, as well as remotely detonated high-explosive shells and other types of IEDs that also have at least a metal fuse. Identification, friend or foe function, is based on multiple sources of user location data, transponder, communication sessions, visual confirmation, or probable location, restricted mission data, route tracker, auto-tasking. In all cases where the user's location must be kept secret, a narrow beam connection between the user and the subnets is made through repeaters whose position is known in advance, located on satellites, airships, and UAVs. Through this connection, the user receives updates on the location of other users whose location is not known to the user. While maintaining ongoing connections with other users, short packs are exchanged periodically to update the current location of the connection points so that the connection is not interrupted. Each user has access to stealth communication within a peer-to-peer network with limited range amplitude, stealth communication with a drone and robot, stealth communication with a command post, stealth communication via satellite or transceiver on a drone robot airship, stealth communication in cross-domain communication with another unit. In case of GNSS signal suppression or distortion, determine the user's own position when direction finding two or more separated beacons whose location is known. Main capabilities for all users: detection, identification, tracking, localization, aiming assistance and transmission to the command center of the coordinates of the direct signal source, portable and stationary radio transmitting station, radar, drone, robot, drone, or robot operator, radio beacon, as well as the source of the reflected signal, vehicles, small arms, including hidden underclothing, enemy personnel, buried and unburied mines, and IEDs. Given the prospect of enemies developing AI technologies and direction-finding capabilities, the use of omnidirectional antennas increases the threats to military use. At the same time, the development of narrow-directional radio technology reduces these risks. The project contains many innovations and a certain number of inventions. As of today, we are not aware of analogs as a comprehensive system, including for mobile platforms, which may be ready in the next 2 to 3 years. We are aware of examples of prototypes and statements from corporations and startups about some elements separately. Some portable systems and systems mounted on vehicles and drones are worthy of interest, but upon detailed examination, even at the concept level, we found significant differences from our designs. Modern design and virtual prototyping technologies: Altium, KiCad, NI LabVIEW, SolidWorks, ANSYS, and MATLAB, which we use, provide opportunities to accelerate the R&D process 10 times faster than in previous years. We focus primarily on components from well-known vendors: Analog Devices, ST Microelectronics, Renesas, Texas Instruments, Intel, etc., to realize radio direction finding technology and other functions. For some elements, such as multi-band antennas for PAA, we are studying the possibility of manufacturing according to our own drawings and technology at specialized production facilities in the USA, Germany, Switzerland, Israel, and Taiwan. We estimate likely technology readiness in 2027 after completion of testing and positive results from pilot projects with USMC and U.S. Army units. Above all, we want our inventions and developments to be useful for defense and national security purposes. We also hope to acquire helpful mentors and advisors from the NGA experts to help us avoid mistakes and wasted time. We are aware of financial opportunities within NGA, including venture capital investment opportunities that could be very beneficial to our project, especially in the early stages. We are also very interested in recommendations and help in networking with other future industry partners to integrate with their projects and to help distribute our project in the future. In particular, we are trying to establish partnerships with Palantir Technologies, Anduril Industries, and other progressive, fast-growing companies in the industry. Thank you for watching.